Hi, so I'm back with the second video. We're going to be talking about molecular geometry this time. Now that we know a little bit more about electron geometry, we're going to be looking at, hey, what happens if we have like electron pairs instead of bonds? And if we have double bonds, triple bonds, does that matter? Actually, I don't know if that matters for this particular course, but I know that it actually does matter just generally. Maybe I should ask her that, like my professor that. Don't remember what she said. Okay, so with molecular geometries, you start with electron pair geometry. And so we look at the steric number again. You know, how many areas of electron density do we have? And then that's our steric number associated with like trigonal, bipyramidal, tetrahedral, octahedral, things of that matter. Then you have to ignore lone pairs. Just only consider the bonded atoms for now. That's like electron pair density. But wait, hold on. Yeah, only when you're looking at electron pair geometry, you're gonna be ignoring the lone pairs when you like first try it out, but then when you go into molecular geometry, you're considering like the distortions from the ideal geometry that you would have had. So non-bonding electron pairs exert a greater repulsive force than bonding electron pairs. Multiple bonds exert a greater repulsive force than single bonds. And so really like all that you really need to know for molecular geometry is not necessarily like the specific angle that you're gonna get by having a certain number of electron pairs, but rather, you know, is it larger than 1 to 9.5? I don't know. Does the electron pair, you know, repulse more than the bond? Yes. So maybe the 1 to 9.5 isn't like 1 to 9.5 anymore, you know? So you're gonna have to be able to like tell them, hey, this angle might be bigger, this angle might be smaller. So for example, when you have I don't know what this is. I think it's okay. So there's like an example in my packet which says like, you know, for an H2O, this is a bet molecule. So you have hydrogen here, and 2 electron or lone pairs. So the steric number is technically 1, 2, 3, 4, right? And so for 4, you would have tetrahedral, and then, okay, but then this is different because it's like a linear molecule except bent, kind of. Don't really know how to describe it. So, okay, in this example it says, it has like this picture that goes like 104.5 degrees. Oh. And then it has an arrow pointing like that, 109.5. And so I guess this is trying to say that like that angle was supposed to be 109.5. Oh, that makes sense. Okay, yeah, that makes sense. So when you have a steric number of 4, I told you that anything with a steric number of 4, it's gonna look like, so here's the central atom, here's your like electron density, and then you have like a tripod thing going on, right? And so H2O has the same exact thing going on. You know, these are just electron densities. They're not exactly like, oh, they have to be lone pairs, or oh, they have to be like hydrogens or atoms. And so, you know, these hydrogens will be here, and your electrons are actually hanging out here. So in a tetrahedral structure, the angles between all of these are supposed to be 109.5. That's where this particular part of the diagram comes from, but it's actually 104.5 because these or like in relation to the atoms off the central atom. So, but these electron pairs are actually like much stronger in pushing away the hydrogens and from each other than just the hydrogens or any bond in general. And so what happens is that they exert greater force, and so these hydrogens get squished together more, because like the electron pairs are like more, they like bully the hydrogens more than the hydrogens bully them. So they're going to be pushed towards each other more, therefore the angle is going to be less. Okay, cool. Alright, that's for 3. Molecular geometries. Steric number of 2 can only be linear. So now we're gonna get to like the specific, like, so you know how I gave you those like generic like electron pair geometries? Well, now there's like, now that we're looking at lone pairs as well, we're gonna be looking at a lot more instances where it's like, oh, but what if this has more lone pairs, or what if it doesn't have any lone pairs at all? What if it's like this, or what if it's like that, right? And so there's a lot more instances in which you have to like question yourself on what exactly this molecule looks like. And so on my cheat sheet, I'm gonna make sure to put this, but so molecular geometry, let's write this down so we know that we're what we're talking about. Molecular geometry, right? So if you have a steric number of 2, that always means that you're going to have that you can only be linear. And it says that it's pretty much like CO2. And I'm thinking that this is because C, and then you have oxygen, oxygen, but carbon loves to have 4 electron like pairs. And so this is probably going to be a double bond, right? I think it'd be better if I like actually did the process here, just to like prove it. So let's look at the Lewis structure, right? So how do we draw the Lewis structure? We're going to start out by going, oh, well, CO2, when we know that the central atom is going to be the least electronegative. And so if we look at the periodic table, the least electronegative, you're going to be finding those farther here, because the most electronegative one is fluorine. And anything that's like more away from fluorine is going to be less electronegative. And so we know that carbon is less electronegative, meaning that like it doesn't mind sharing electrons, because electronegativity is like how much you really want that electron. So for example, if there's just a carbon and an oxygen, the carbon's gonna be like, you can have it. I mean, I'll grab onto this electron, but I mean, you can have more of it. And the oxygen is more demanding than the carbon, and so it wants the electron like closer to it. And so what's gonna happen is that like if you have this kind of bond, right? So you have an electron or electrons here, and the oxygen is going to be more demanding, so the density is going to be like more like that, I feel like. And so it's going to be farther away from carbon and more towards the oxygen. Anyway, what was I talking about? Oh, okay. So central atom is going to be carbon, and then we know that we're going to have oxygens on like whatever side. But what I do is say, okay, so what do these little children want? You know, so carbon wants 8 electrons in its valence shell. So does oxygen. But remember that there are 2 oxygens here. So accounting for the fact that there are 2, you know, what do these little children want? They want 3 times 8 electrons in their valence shell. And so that's going to be 24. So now what do these children actually have, right? So what do they want versus what do they have, and how much are they gonna have to share between each other? That's what I'm trying to figure out. So carbon, with an atomic number of 6, but also 1, 2, 3, 4, it's gonna have 4 valence electrons. So carbon has, so here, I'll make like a chart. Carbon has 4 valence electrons. Oxygen, on the other hand, has 6. Now remember that there are 2 of them, so they're going to have 2 times 6, which is 12, plus 4 is 16. So this is what they want. This is what they actually have. So in order for everyone to be satisfied, we're going to have to find the difference between these two, right? So we're going to have to look at our budget. 26 minus 16, carry over, this is going to be 8. So we're going to have 8 electrons between all of the atoms, eight electrons that are bonded in bonds. Yeah, 8 electrons in bonds. And so carbon is the central atom. You have oxygen somewhere here, or somewhere here. It doesn't matter at this point, but since we're looking at a Lewis dot, we're not gonna make the assumption, we're not gonna like put this oxygen up here just because we don't want to make assumptions on like where it actually is. So we're just gonna keep it simple, put it here. 8 electrons are made or used in bonds between these 3 atoms, and so in order to use up 8, and each bond is worth 2 electrons, and so 1, 2, 3, 4, 5, 6, 7, 8, and so that's all that they have to share. And so now we have 16 that we had from all of these atoms. We have 8 that we used already. So that's you're gonna have to use 8 electrons for lone pairs, right? So 1, 2, 3, 4, 5, 6, 7, 8. Are they all happy? Let's check. Oxygen, this child has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Carbon also has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Oxygen here has the same thing, so they're all satisfied. Let's count if they all add up to 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We used up all 16 of the electrons that the CO2 had. And so, since there are like no lone pairs on this, since this has a steric number of 2, because this carbon has 2 electron densities next to it, and so since it's a steric number of 2, it's going to be linear. If this carbon, for some whatever odd reason, maybe these weren't oxygens or something, but if it was just like, if it had like a lone pair here or something, that'd be 3 electron densities, and that would no longer be a linear molecule. So, but in this case, when we have a steric number of 2, it's going to always be linear. Next one. I don't know if I'm actually like taking the proper amount of time to explain all these, but I'm going to like just try to like go through all of them. All of the things that I can like remember. So if you have steric number of 3, you have 2 different types of molecules that you can, excuse me.